This final set of practices, called pressing for evidence-based explanations, is used near the end of a unit. One of the practices involves students developing a final set of claims about the anchoring event and learning how to use evidence to support those claims. The other practice asks students to create a final explanatory model in both drawn and written forms that integrates ideas from multiple activities and readings throughout the unit. These two practices can be used in either order, depending upon how you'd like to coordinate students' intellectual work.
In this practice, kids are asked to really draw on a lot of activities that they've done and to try to make sense out of them as a whole to produce this explanation. So what kinds of work do you want kids to do when you do these kinds of lessons?
So when we are trying to sort of put it all together, there's two main things that I push students to do, and I typically separate them right now just because they both require a lot of work. And ideally I would want kids to be able to integrate them. So maybe that's an 8th grade year goal. The first one is being able to write or draw an explanation, a cohesive explanation, as cohesive as possible. So just take the initial question, and now that you've spent 3 weeks learning about this, explain to me what's happening. And typically we have a lot of supports for this, like we'll make a checklist of ideas that need to be included, but they're never complete. They're phrases or words or things like that. And so part of that goal is being able to write and communicate, and part of that goal is piecing together ideas and integrating ideas and sequencing ideas. That's an important one. Knowing where you start with an explanation and what pieces are related to what other pieces, where they go. But then the other big practice that I'm really trying to push with these kids is getting them to use evidence to back up all those pieces. So not just using evidence, but being able to map it onto their explanation and say, you'll see in my classroom, you'll see a lot of models that have paper on the outside that has an arrow drawing into the explanation or to the model and saying, I know this because, or I know this because. And
do you use sentence frames for that?
Yes, usually. Yeah, usually just, I know this because, or if I feel like there's a class activity, I know this because in class we blah, blah, blah. Or the activity that proves this to me is blank because. So really basic sentence frames. But I try not to limit it to class also, because, for example, the kid the first day might be able to explain collecting the distillate on the other side with his TV show, you know, and that totally counts because, you know, evidence comes in different forms, and the important piece is that you're not just making claims, but you're backing up your claims, which I think is a real authentic science practice.
You had used, speaking of kids' ideas, counting as a science idea. You had one young man who wanted to act out molecular movement, and they came up with this domino theory.
Yeah.
And so that ended up showing up in people's models at the end, that that little domino theory by one of your students became a legitimate science idea, right?
Right. And like I said to them almost every day after that, that's a student that just constructed science, right? It's science that someone else has already come up with, right? You'll find that idea of molecules hitting molecules and likening it to dominoes, someone's already said that, but you didn't hear that. You came up with that on your own. So it's just sort of allowing them to be scientists, because that's what we do.
At this point in the unit, Anna's students have completed their summary table as a public representation of what they know. Each row represents an activity with its own model, what students have learned from it, and how they think it helps explain the anchoring event. Anna now asks students to use these ideas to revise their whole class model.
Here's a good example. The solid melts into the liquid, it gets hotter. Okay? That was how someone explained what melting was on day 1. So if you think you are melting down, you're going to take this back to your seat. Then you're going to take an orange Post-it, and you're going to revise this person's explanation. So they have said that melting is when a solid turns into a liquid. Yes, that is true. They're not wrong. And they've said that it takes heat to do it. That sounds reasonable to me. So you need to look at what they have that's good. Think about what they're missing. And you're going to rewrite a new post-it that has all of it. Because what we're doing right now is we're doing real science. We're going back to our ideas and we're thinking about the new information we have and we're revising them. We're making them better. We're adding detail. Maybe we're adding a picture. You might find post-its up here that don't really need to be revised. Don't choose those. Leave them up there. Choose the post-its that we need to modify, that we need to change.
I read more than 3 miles. He's got me too.
This one said in the hot water molecules are everywhere, in cold water molecules are slower.
Okay, so what are you changing it to?
And hot water molecules are less attracted from each other and they move very fast, bumping and hitting, passing the heat. And the cold water molecules are very attractive, moving slower.
That was your idea, wasn't it?
Yeah.
That's what I thought.
After students revise their whole class model, we can see if and how their thinking has changed. On the before sticky notes, we can see that many students had already been exposed to the idea that molecules in a solid move more slowly than those in a liquid. But these understandings appear limited in their applicability to all parts of the distillation phenomena. When we look at the orange sticky notes applied near the end of the unit, we still see some evidence that students have not developed explanations for parts of this anchoring event. Other stickies, however, reveal distinct changes in thinking and language use. The orange sticky on the right describes key events starting not in the flask, but in the hot plate, and describes a chain reaction of faster-moving molecules. This sticky tells about the attraction between molecules and how it weakens with distance. This note clarifies a misconception many students had earlier and states correctly that steam is composed of evaporated water molecules. Perhaps the most impressive idea was written over 3 connected stickies. On these notes, the student claimed to have a viable theory for the brown syrup left over in the distillation flask. She or he believed that the brown material's molecules contain more atoms than the water. These, the student reasoned, were analogous to a heavy person who would require more energy to move than a lighter person.
Question number 1 says, what makes a good explanation or a good model? If that is a hard question for you to understand, then move down to these bullets and try to use them to answer that question. Think about the first post-it, the one you pulled off. Some of you read them and you were like, this does not tell me anything. What did you change? What did you add to it? Or what was it missing? So what did you have to do to make a good explanation on that orange post-it that was different from the first post-it?
In the last small group activity of this unit, Anna gives students a reduced template of the distillation model. She asks students to select 4 activities they had done during the unit and write out how each provided evidence for a part of the distillation explanation. The students' work told her that they needed to have a whole class conversation about evidence and the kinds of explanations she would expect from them.
All right, so all we're going to do is, I'm just going to draw names. I just want you to tell me one thing you've heard, either from your partner, that you wrote down, that you heard someone else say. My goal is to not be back here longer than like 7 minutes, so this should be really, really fast. Okay? Curtis,
What's up?
what makes a good explanation or model?
Evidence from the word wall or summary table.
Okay, I didn't hear that before, so I like that you included the summary table. Anything similar? Any other resource to add to this that you might use as evidence? Your notebook? Your journal's a big one. The summary table is just like a quick version of your journal, right? Thanks, Solano. Let's get a couple more. Asia. She's done.
Yeah.
Alex, what's something else? Okay. So maybe let's think about the explanation itself. What do you think you need to include in an explanation for it to be good, besides evidence?
Money.
Words? What kind of words? Scientific words. See, you were joking, but that's actually a really good one. So Trung just brought up something really, really good. He said we had to write about molecules, and he said we can't see molecules. So maybe including information about things you can't see. Missing. Raise your hand if you think there's something missing that you would like added. Who?
Details.
Details. Oh.
Incorrect information.
Oh, that's.
So I'm going to put that as a second one, and I'm going to say check facts. What counts as good evidence? And this is a reminder that if you are in this space and you are not sharing your ideas, you're at a voice level 0.
Good lecture.
Yeah, like that's what we call when you give an academic lecture. Alana, you had your hand up next. Observations.
Yeah, that's good.
Pictures.
Okay. Got the summary table up here. What's the one thing that's missing?
Oh, right here. I got
Holler
you.
it out.
A journal.
Hallelujah.
Right.
For students' final individual assessments, they were asked to provide a full explanation not only for the distillation, but for the separate activities done during the unit. This will not be the last time students use these ideas. They will apply these to new and different scenarios at the beginning of the next unit.